welcome to this video. Today we're going to talk about the Keccak algorithm. This algorithm is a submission to the NIST open call for the SHA-3 standard. The NIST requires that all the submissions must support at least 4 different kinds of output lengths. So the Keccak algorithm here supports these 4 different kinds. So the output length n can be 224 or 256 or 384 or 512. And the algorithm Keccak is defined with 2 parameters R and C, and this symbol here indicates the truncation of the outputs. So for the n equals to 256, this is a Keccak 256 algorithm, which is widely used in the Ethereum. And so we will take the first 256 bits of the outputs of this algorithm as the final hash value. So let's see the parameters. N is the output length, and R here is the bit rate, which is the number of bits we're gonna process in each round in the algorithm of the message, of course. And the C here is the capacity, which is related to the security level. Well, the algorithm, the details and the structure are the same for these four different kinds, but the parameters are different. And so now let's see what the Keccak function is. It's actually a sponge function which defined like this. So first we're gonna need a permutation function f in this algorithm, and also a padding rule is defined, and the bit rate is given in this function. So this picture here is from the Wikipedia, and it shows the details of this function. Why it's called a sponge function is because we're gonna first absorbing the message bits, and then we're squeezing out the output as the final hash value. In these two phases, the process pretty much the same, just slightly different, and the same permutation function f is used in both phases. Now let's see how the function actually works. So first we're gonna need some padding, and as defined here, we will pad the message. Start with the bit 1 and many zeros, and end it with another bit of 1. So this is officially defined like this, and the final length will be a multiple of R. And then we're gonna divide the message into R-bit blocks. So for each of these blocks, they have R bits, and suppose there are in total n blocks, and then we're gonna enter the absorbing phase to process these message blocks. So first we're gonna need a state S, and we initialize it as b bit of zeros. So like here, well, b is equal to R plus C. By default is equal to 1600, and we denote it as the state size. So this is the initial state S. They're all zeros, and then we process the message blocks. So for each block pi, we first gonna pad it with another b minus r 0 bits, so that the in total length will becomes b bits. So that's 1600, and then we gonna we're gonna XOR this message with the state S, and we get the state becomes S, and then we pass it to the permutation function F and get the result as the state S for the next block. So we process P1 after that, and finally we're gonna process all these M blocks and arriving at the state as here. So then we enter the squeezing phase. First we're gonna output the first R bit of the state as Z0. And if the length of Z0 is larger than the output length N, so we're gonna just we're gonna let Z equal to Z0, and we output the first N bit of Z as the hash value of the Keccak hash function. So like in the Keccak 256 algorithm, the R here is 1088. So actually for the first Z0, the length will be R bit, so it's 1088 bit. And the output length is 256. So we're gonna just use the first 256 of 0, and of course that's as the final hash value of Keccak 256. But for other cases, if the length of Z0 is less than the output length, we're gonna pass the state into the permutation function and get the next state, and we also output the first R bit as Z1, and then we add Z0, Z1, we put them together, and we will see if the length of the output Z is enough for the output. Then we're gonna output the N bit of Z. If not, we're gonna process the state by another round of the permutation, and to get the next output Z2, like that, until we get enough bit for the output. So that's the process for this sponge function. Now let's get into the details of the permutation function F. F is a permutation function of NR rounds of R. We will explain what is NR and what is the capital R later. So first let's consider the state S. During the process we just introduced, we always have the state S, which has 1060 bits, and actually this bit string can be mapped into an X times Y times Z array of bits. So in this picture here, for example, we use X, Y, and Z coordinates. So X can be 0 to 4, so in total 5 values, and Y can be also be 0 to 4, so in total 5 values, and Z here can be 0 to 2 to the power of L minus 1. And since by default the length of the state is 1600, so we're gonna need the 5 times W here must be 1600, and so that the W must be 64. And since W is the 2 to the power of L, the value L must set to 6. And for the number of rounds NR is defined as 12 plus 2 times L, so it's 24. And so this permutation function will need 24 rounds of R here, and R is function defined like this. So there are in total 5 functions in this operation, and they are defined here respectively. And since we have mapped the state S to the state A, so this actually the input of the A is actually the state bit, and the mapping rule is like this. So for the the bit AXYZ, the corresponding bit is W times 5 times Y plus X plus Z, is this bit in the state S. So for these 5 functions, we are not gonna explain the details about them. There are some operations in addition and multiplication of the matrix, and these operations are defined in the field GF2. And for the last function, the alpha function, we're gonna need a round constant RC, and for each round IR, we're gonna use a different constant. And this constant value is actually the output of a bit LFSR, which is short for linear feedback shift register. If you're interested, you can study the details about these functions in the submission of this Keccak algorithm, and also find the details in the Wikipedia and both some GitHub project for the program of this algorithm. So due to time limit, we will end this video here. Thanks for watching. See you.